Learning objectives. In this chapter, the user would learn the following in detail. TMS 320 C40 bar 50. Analog devices. Introduction. The natural environment that we wish to interpret is analog. Signals vary continually with time and may feasibly take any value. The digital domain is fixed between two values, high and low. Conversion from the analog domain to the digital domain and back is essential to sense signals, manipulate them, and reintroduce them to the environment. The advantages gained from digital manipulation justify the conversion. Special devices that perform from this conversion are manufactured to interface with DSPs. This chapter introduces such devices and discusses about a few of them in detail, listed below. TMS 320C40, TMS 320C50, Shark and Tiger Shark processors, Blackfin processor, ADSP21XX processors. Analog devices. Analog devices as an expanding portfolio of DSP's mixed signal control processors, embedded processors, and analog microcontrollers for a wide variety of general purpose and application specific needs. Digital signal processors DSP take real world signals like voice, audio, video, temperature, pressure, or position that have been digitized and then mathematically manipulate them. A DSP is designed for performing mathematical functions like add, subtract, multiply, and divide very quickly. In the real world, analog products detect signals such as sound, light, temperature, or pressure and manipulate them. Converters such as an analog to digital converter then take the real world signal and turn it into the digital format of ones and zeros. From here, the DSP takes over by capturing the digitized information and processing it. It then feeds the digitized information back for use in the real world. A few examples of analog devices are Shark, Tiger Shark, Blackfin processors, ADSP21XX. Blackfin processor embody a new breed of 1632-bit embedded processor ideally suited for products where a convergence of capabilities are necessary, multi-format audio, video, voice and image processing. Shark or processors dominate the floating point digital signal processing market, delivering exceptional core and memory performance complemented by outstanding input-output throughput. Starting at 319 MF lobes per dollar. Shark brings floating point processing performance to applications where dynamic range is key. Tiger Shark processor provide the highest performance density for multi-processing applications with peak performance well above a billion floating point operations per second. ADSP21XX processors are code and pin compatible families of digital signal processors with performance up to 160 MHz and power as low as 184 microamps. The ADSP21XX family is ideal for speech processing and voice band modems as well as real-time control applications. Sigma DSP. The Sigma DSP processors are fully programmable single chip audio DSPs that are easily configurable through the Sigma Studio graphical development tool and are ideal for automotive portable audio markets. Sigma DSP chips are available with integrant sample rate converters, ADCs, DACs, and output amplifiers. Shark processor. Processor from analog devices. SHARC stands for Super Harvard Single Chip Computer. Super Harvard architecture means more than one set of address and data buses for data. For example, set J of address and data buses for data memory space, set K of address and data buses for data memory space, and set I of address and data buses for program memory space. SHARC functions. Program memory configurable as program and data memory parts. Princeton architecture. SHARC functions as VLIW, very large instruction word, processor, used in large number of DSP applications. Controlled power dissipation in floating point ALU. Different SHARCs can link by serial communication between them. SHARC features: on-chip memory 1 MB program memory and data memory, Harvard architecture. External off-chip memory. Off-chip as well as on-chip memory can be configured for 32-bit or 48-bit words. Integer operation features: integer and saturation integer arithmetic both. Saturation integer example: integer after operation should limit to a maximum value required in graphic processing. Parallel processing features: supports processing instruction level parallelism as well as memory access parallelism, multiple data access in a single instruction. Addressing features: SHARC 32-bit address space for accesses. Accesses 16 GB or 20 GB or 24 GB as per the word size, 32-bit, 40-bit or 48-bit, configured in the memory for each address. When word size equal to 32-bit, then external memory configuration addressable space is 16 GB, 2 power 32 into 4 bytes. Word size features: provides for two word sizes, 32-bit and 48-bit. SHARC two full sets of 16 general purpose registers. Therefore, fast context switching allows multitasking OS and multi-threading. Registers are called R0 to R15 or F0 composite F15 depending upon integer operation configuration or floating point configuration. Registers are of 32-bit. A few registers are special of 48 bits that may also be accesses as pair of 16-bit and 32-bit registers. SHARC features: instruction word 48 bits, 32-bit data, word for integer and floating point operations, 40-bit extended floating point. Smaller 16 or 8-bit must also store as full 32-bit data. Therefore, the big endian or little endian data alignment is not considered during processing, with carry also extended for rotating RRX. Tiger Shark processor: highest performance density family of processors from analog devices. Precision high performance integrated circuits used in analog and digital signal processing applications. Designed for multiprocessing and applications and for peak performance greater than BF lobes, billion floating point operations per second. Example: ADSP TS203 SABP 050 processor processes using 250 MHz clock and on-chip memory of 6 megabits and operates at 1.2 volt, 3.3 volt. Low voltage design helps in processing with little power dissipation. Analog devices claims the highest performance per watt. Tiger Shark. Multiple Tiger Sharks can connect by serial communication at 1 Gbps. A Tiger Shark version has 24 Mbits on-chip memory, 2 ALUs and 2 set of address and data buses for data memory, on set of address and data buses for program memory. Tiger Shark is available as IP core also so that new applications and enhancements can be developed. Shark generations. First generation Shark products offer performance to 66 MHz, 198 MF lobes and form the cornerstone of the Shark processor family. They are easy to use instruction set architecture that supports both 32-bit fixed point and 32/40-bit floating data formats combined with large memory arrays and sophisticated communications ports make them suitable for a wide array of parallel processing applications including consumer audio, medical imaging, military, industrial, and instrumentation. Second generation Shark products double the level of signal processing performance, 100 MHz bar 600 MF lobes, offered by utilizing a single instruction multiple data SIMD architecture. This hardware extension to first generation Shark processors doubles the number of computational resources available to the system programmer. Second generation products contain dual multipliers, ALUs, shifters, and data register files, significantly increasing overall system performance in a variety of applications. This capability is especially relevant in consumer, automotive, and professional audio, where the algorithms related to stereo channel processing can effectively utilize the SIMD architecture. Shark generations. Third generation Shark products employ an enhanced SIMD architecture that extends CPU performance to 450 MHz bar 2700 MF lobes. These products also integrate a variety of ROM memory configurations and audio-centric peripherals designed to decrease time to market and reduce the overall bill of materials cost. This increased level of performance and peripheral integration allow third generation Shark processor to be considered as single chip solutions for a variety of audio markets. The fourth generation of Shark processors now includes the ADSP 21486, ADSP 21487, ADSP 21488, ADSP 21489 and offers increased performance hardware based filter, accelerators, audio and application focused peripherals and new memory configurations capable of supporting the latest surround sound decoder algorithms. All devices are pin compatible with each other and completely code compatible with all prior Shark processors. These newest members of the fourth generation Shark processor family are based on a single instruction multiple data SIMD core which supports both 32-bit fixed point and 32/40-bit floating point arithmetic formats, making them particularly suitable for high performance audio applications. Blackfin processor, made by Analog Devices Corporation, a new breed of embedded media processor designed specifically for today's embedded audio, video and communication applications. Combine a 32-bit RISC like instruction set and a dual 16-bit multiply, accumulate, MAC, signal processing functionality. Perform equally well both in signal processing and control processing applications, in many cases deleting the requirement for separate heterogeneous processes. Architecture basics. The two 16-bit MACs, two 40-bit ALUs, 4 8-bit video ALUs, support for 8 bar, 16 bar, 32-bit integer and 16 bar 32-bit fractional data types. Concurrent fetch of one instruction and two unique data elements. Two loop counters that allow for nested zero overhead looping. A modified Harvard architecture in combinational with a hierarchical memory, arbitrary bit and bit field manipulation, insertion and extraction, two data address generator DAG units with circular and bit reversed addressing. Data address generator contains two 32-bit address ALUs and an address register file. Address register file consists of 6 32-bit general purpose pointer registers and 4 32-bit circular buffer addressing registers. Unified 4GB memory space. Mixed 16 bar 32-bit instruction encoding for best code density. Memory protection for support of OS operation. Architecture basics. 3 modes of operation. User mode. User mode has restricted access to a subset of system resources, thus providing a protected software environment. User mode is considered the domain of application programs. Supervisor mode, emulation mode. Supervisor mode and emulation mode have unrestricted access to the core resources. Supervisor mode and emulation mode are usually reserved for the kernel code of an operating system. Memory architecture. A single unified 4G byte address space using 32-bit addresses. The L1 memory system is the primary highest performance memory available to the core and is faster than L2 memory system. The L2 memory system is off-chip and have longer access latencies. ADSB 21XX processors. A collection of programmable single-chip microprocessors that share a common base architecture optimized for digital signal processing DSP and other high-speed numeric processing applications. The various family processors differ principally in the type of on-chip peripherals they add to the base architecture. On-chip memory, a timer, serial ports and parallel ports are available in different members of the family. In addition, the ADSP 21MSP58/59 processors include an on-chip analog interface for voice band signal conversion. Functional units. Computational units. Every processor in the ADSP 2100 family contains 3 independent full-function computational units, an arithmetic logic unit ALU, a multiplier accumulator MAC, and a barrel shifter. The computational units process 16-bit data directly and also provide hardware support for multi-precision computations. Data address generators and program sequencer. Two dedicated address generators and a program sequencer supply addresses for on-chip or external memory access. The sequencer supports single-cycle conditional branching and executes program loops with zero overhead. Dual data address generators allow the processor to generate simultaneous addresses for dual operand fetches. Together, the sequencer and data address generators keep the computational units continuously working, maximizing throughput. Memory. The ADSP 2100 family uses a modified Harvard architecture in which data memory stores data and program memory stores both instructions and data. All DSP 2100 family processors contain on-chip RAM that comprises a portion of the program memory space and data memory space. The speed of the on-chip memory allows the processor to fetch two operands, one from data memory and one from program memory, and an instruction from program memory in a single cycle. Serial ports. The serial ports provide a complete serial interface with hardware compounding for data compression and expansion. Both MULA and ELA compounding are supported. The ports interface easily and directly to a wide variety of popular serial devices. Each port can generate a programmable internal clock or accept an external clock. Port 0 includes a multi-channel option. Timer. A programmable timer or counter with 8-bit prescaler provides periodic interrupt generation. Host interface port. Host interface port HIP allows direct connection with no glue logic to a host processor. The HIP is made up of 16 data pins and 11 control pins. The HIP is extremely flexible and has provisions to allow simple interface to a variety of host processors. DMA ports. The ADSP 2181's internal DMA port IDMA and byte DMA port BDMA provide efficient data transfers to and from internal memory. The IDMA port has a 16-bit multiplexed address and a data bus and supports 24-bit program memory. The IDMA port is completely asynchronous and can be returned to while the ADSP 2181 is operating at full speed. The byte memory DMA port allows boot loading and storing of program instructions and data. Analog interface. The ADSP 21 MSP 58/59 processors include on-chip circuitry for mixed analog and digital signal processing. The circuitry includes an analog to digital converter ADC, a digital to analog converter DAC, analog and digital filters, and a parallel interface to the processor's core. The converters use Sigma Delta technology to capture data samples from a highly oversampled signal. The ADSP 2100 family architecture exhibits a high degree of parallelism tailored to DSP requirements. In a single cycle, any device in the family can generate the next program address, fetch the next instruction, perform one or two data moves, update one or two data address pointers, perform a computation. In that same cycle, processors which have the relevant functional units can also receive and or transmit data via the serial ports, receive and or transmit data via the host interface port, receive and or transmit data via the DMA ports, receive and or transmit data via the analog interface. DSP performance. Signal processing applications make special performance demands which distinguish DSP architectures from other microprocessor and microcontroller architectures. Not only must instruction execution be fast, but DSPs must also perform well in each of the following areas. Fast and flexible arithmetic. The ADSP 2100 family base architecture provides single cycle computation for multiplication, multiplication with accumulation, arbitrary amounts of shifting, and standard arithmetic and logical operations. In addition, the arithmetic units allow for any sequence of computations so that a given DSP algorithm can be executed without being reformulated. Extended dynamic range. Extended sum of products common in DSP algorithms are supported in the multiply, Accumulate units of the ADSP 2100 family. Single cycle fetch of two operands. All members of the ADSP 2100 family are able to sustain two operand data through put, whether the data is stored on chip or off. Hardware circular buffers. The ADSP 2100 family base architecture includes hardware to handle address pointer wraparound, simplifying the implementation of circular buffers both on and off chip and reducing overhead, thereby improving performance. Zero overhead looping and branching. The program sequencer in the ADSP 2100 family supports looped code with zero overhead, combining excellent performance with the clearest program structure. Computational units. Every processor in the ADSP 2100 family contains three independent full-function computational units: an arithmetic logic unit ALU, a multiplier accumulator MAC, and a barrel shifter. The computation units process 16-bit data directly and provide hardware support for multi-precision computation as well. The ALU performs a standard set of arithmetic and logic operations in addition to division primitives. The MAC performs single cycle multiply or add and multiply or subtract operations. The shifter performs logical and arithmetic shifts, normalization, denormalization, and derive exponent operations. The shifter implements numeric format control including multi-word floating point representations. The computational units are arranged side by side instead of serially, so that the output of any unit may be the input of any unit on the next cycle. The internal result or bus directly connects the computational units to make this possible. All three units contain input and output registers which are accessible from the internal memory data DMD bus. Computational operations generally take their operands from input registers and load the result into an output register. The registers act as a stop over point for data between memory and the computational circuitry. This feature introduces one level of pipelining on input and one level on output. The OR bus allows the result of a previous computation to be used directly as the input to another computation. This avoids excessive pipeline delays when a series of different operations are performed. TMS320C40. The TMS320C4X devices are 32-bit floating point DSPs optimized for parallel processing. The C4X family combines a high-performance CPU and DMA controller with up to 6 communication ports to meet the needs of multiprocessor and input-output intensive applications. Key applications of the C4X family include 3-dimensional graphics, image processing, networking, and telecommunications base stations. Introduction. All C4X devices are compatible with TI's multi-chip development environment. Each device contains an on-chip analysis module that supports hardware breakpoints for parallel processing development and debugging. The C4X family accepts source code from the TMS320C3X family of floating point DSPs. TMS320C4X key features. Key features of the TMS320C4X generation are as follows: up to 30 MIPS and 60 MFLOPS, performance with 384 megabytes input-output capability, IEEE floating point conversion for ease of use, register based CPU, single cycle byte and off word manipulation capabilities, divide and square root support for improved performance. On-chip memory includes 2K words of RAM, 128 words of program cache, and a bootloader. Two external buses providing an address reach of up to 4 GHz. Two memory mapped 32-bit timers. 6 and 12 channel DMA. Up to 6 communication ports for multi-processor communication. Idle mode for reduced power consumption. Optimizing ANSI C compiler. TMS320 C4X CPU. The C4X as an independent multiplier and accumulator and achieves up to 60 MFLOPS. Results are stored in any one of 12 extended precision registers. These are 40-bit registers that store values with a 32-bit mantissa and an 8-bit exponent. These registers can serve as both the source and destination for any arithmetic operation. The extended precision registers are an extremely valuable resource for programming in assembly or C. These registers allow maintenance of intermediate results without storing data in memory. This results in high performance assembly code and an efficient C compiler. To sustain 60 MFLOPS, the CPU has two independent auxiliary register arithmetic units, ARAUs, which can generate two addresses in a single cycle. The two ARAUs operate in parallel with the multiplier and ALU. They support addressing with displacements, addressing with index registers, IRO, and IR1, circular addressing, and bit reversed addressing. Features of the C4X CPU are high-speed internal parallelism, 8 operations per cycle for maximum sustained performance. Floating point integer multiply, floating point integer addition, 2 data accesses, 0 overhead branch and loop counter update. IEEE floating point conversion, divide and square root support for improved performance, single cycle byte and off word manipulation capabilities, register based CPU, TMS320 C4X memory and bus structure. To realize the full performance of the C4X CPU, it is important to have a bus and memory architecture that can keep pace. The C4X fetches up to 4 32-bit words each cycle, a program opcode, 2 CPU data operands, and a DMA data transfer. The internal buses can transfer all 4 words in parallel, relying on 7 memory sources for data. The C4X uses 7 internal buses to access on-chip resources. Program address data. The CPU uses these buses to maintain instruction fetches every cycle. Data address data. In any cycle, the CPU can fetch 2 data operands because it has 2 data address buses and 1 data bus that can be accessed twice in a single cycle. DMA address data. The DMA uses these buses to perform DMA transfers in parallel with the CPU operation. With the internal buses in place to feed the DMA and the CPU, the C4X devices can use both internal and external data and program memory. Internally, the C4X has two 1K by 32-bit word blocks of dual access RAM, providing up to 4 words of program or data in a single cycle. For external memory, the C40 has two identical 32-bit buses which address up to 2G words of memory each. The C44 has two 24-bit external address buses which address up to 16 M words each. Each device has an on-chip instruction cache to boost performance when using slower external memory. TMS320C4X communication ports. The communication ports on this C4X generation transfer up to 24 megabytes each for asynchronous interprocessor communications or for servicing intensive application needs. The C40 has 6 ports and the C44 has 4. Each port has 4 control pins and 8 data pins. These 12 pins provide a glueless interface to another C4X. The control pins combined with the control logic arbitrate with another device to determine data transfer, timing and direction. Because the communication ports have built-in arbitration and control circuitry, you simply need to read data from and write data to the memory mapped input and output FIFOs. In a typical transfer, the DMA coprocessor or the CPU first writes to the output FIFO. Next, the communication port sends a request signal to the destination processor which responds with an acknowledge. The communication port then transfers the word as 4 successive bytes. The destination processor receives the word in its input FIFO where the destination DMA or CPU can read the contents. Note that the input and output FIFOs provide a 16 word by 32-bit buffer between the communication ports. Features of the C4X communication ports include up to 24 megabytes bidirectional interface on each communication port for high speed and low cost parallel processor interface, 8-word deep input FIFO and 8-word deep output FIFO buffer, automatic arbitration and handshaking for direct processor to processor connection. TMS320C4X DMA coprocessor with as many as 6 communication ports and 2 external buses. The C4X has an input and output capability of as much as 384 megabytes. To service this tremendous speed, the C4X has a 6 or 12 channel DMA. The DMA operates independently of the CPU and has dedicated address and data buses to avoid bus conflicts. The DMA is programmed to transfer data from any memory location to any other memory location. Communication ports are memory mapped. The DMA can begin a task based on CPU or external interprets and can interpret the CPU at the completion of a task. The DMA also includes a link pointer register that allows the DMA to program its next task without CPU intervention. Since each communication port has transmit and receive capability, 12 DMA channels are needed if all 6 communication ports are being used in a bidirectional mode. The DMA has a split mode operation dedicated to this function, allowing the DMA to service the 12 input-output FIFOs in the communication ports. In the event that both the CPU and DMA access the same resource, priorities can be assigned to resolve the conflict. Priority can be assigned to the CPU, the DMA, or mixed where the CPU gets the first access followed by the DMA. The C4X DMA coprocessor features concurrent input-output to maximize sustained CPU performance. Auto initialization up to 6 or 12 DMA channels for parallel data transfers. Data transfers to and from anywhere in memory. 3 operations per cycle. 32-bit data transfer, address register update, transfer counter update, performance of 90 MOPS. TMS320 C40. The C40 is the original member of the C4X family. It features a CPU that can deliver up to 30 MIPS and 60 MFLOPS with a maximum input-output bandwidth of 384 megabytes. The C40 has 2K words of on-chip RAM, 128 words of program cache, and a bootloader. 2 external buses provide an address reach of 4G of unified memory space. The C40 is available in a 325-pin PGA. Features of the C40 include 33 and 50 numbers instruction cycle times, 4G word external address reach, optimizing ANSI compiler, IEEE floating point conversion for ease of use, 6 or 12 channel on chip DMA, 6 communication ports, accepts source code from C3X. TMS320 C44. The C44 is a lower cost version of the C40 used for parallel processing applications that are more price sensitive. The C44 features 4 communication ports and has an external address reach of 32 M words over 2 external buses. To further reduce cost, the C44 comes in a 304-pin PQFP. The TMS320C44 can deliver up to 30 MIPS, 60 MF LOPS performance with a maximum input-output bandwidth of 336 megabytes. The C44 is source code compatible with the C40. Features of the C44 include 33 and 40 numbers, instruction, cycle times, idle mode for reduced power consumption, optimizing ANSI compiler, IEEE floating point conversion for ease of use, 6 or 12 channel on chip DMA, 304-pin PQFP 388 BGA, 32 M word external address reach, 4 communication ports, TMS320 C50. The TMS320 C5X generation is TI's most widely used fixed point DSP. The C5X devices offer performance of 20 to 50 MIPS with power consumption reduced to 2.35 MIPS for typical applications. The 3V versions maintain 40 MIPS performance and reduce power consumption to 1.15 MIPS. Introduction. A programmable software wait state generator has been added to the C5X, allowing interfaces with up to 7 wait states. Wait states are programmed on 8K word boundaries, allowing the designer to optimize memory configuration for performance and cost. The standard serial port operates at up to 12.5 Mbps. This is a synchronous double buffered serial port with independent transmit and receive sections. The time division multiplexed TDM serial port has all the same features as the standard serial port with the addition of time division multiplexing. This will make it well suited for inter-processor communication in multi-processor DSP systems. The buffered serial port comprises a full duplex double buffered serial port interface and an auto buffering unit. The BSP operates at up to 40 Mbps with no CPU intervention. The serial port interface block of the DSP is an enhanced version of the standard serial port interface. The host port interface HPI is an 8-bit parallel port used to interface a host device to the C5X. HPI memory is a 2K by 16-bit single access RAM SARAM block that can also be used as general purpose on chip or program SARAM. Multiple on chip based locked loop PLL options are available depending on which C5X is chosen. The PLL allows designers to maintain CPU speed but use a slower external clock frequency. This reduces power and electromagnetic emissions. For systems requiring significant off-chip resources, the C5X family addresses 64K by 16 bits in program data and input-output spaces. Each uses its own select pin. TMS320C5X key features. Following are the key features of the TMS320C5X generation. When only certain devices have a particular feature, they are named in parentheses following the feature's description. CPU 20ns single cycle instruction execution time 50 MIPS. 25ns single cycle instruction execution time 40 MIPS. 35ns single cycle instruction execution time 28.6 MIPS. Single cycle multiply accumulate MAC for program code. Single cycle single word repeats and block repeats for program code. Block memory moves for good program data management. 4-level deep executable pipeline to handle delayed branch call and return instructions. Indexed addressing mode. Bit reversed indexed addressing mode to facilitate fast Fourier transforms FFTs. Power down modes. 32-bit ALU, 32-bit accumulator and 32-bit accumulator buffer. 8 auxiliary registers with a dedicated ALU for indirect addressing. 16-bit parallel logic unit PLU for fast bit manipulation. 16 by 16-bit parallel multiplier with a 32-bit product capacity. So 16-bit right and left barrel shifters. 64-bit incremental data shifter to indirectly address the circular data buffers for circular addressing. Peripherals. 8-level hardware stack. 11 context switch registers to shadow the contents of the strategic CPU controlled registers during interrupts. Full duplex synchronous serial port which directly interfaces to the codec. Time division multiplexed TDM serial port C50, C51, C53. Buffered serial port BSP LC56, LC57, BC57S, C57S, LC57S. Interval timer with period and control registers for software stops, starts and resets. Concurrent external DMA performance using extended holes. On-chip clock generator. Various phase locked loop PLL options for reduced EMI and system power dissipation. PLL clock generator X1, X2, X3, X4, X5, X9. LC56, LC57, BC57S, C57S. IEEE 1149.1 Standard JTAG Scan Path Test Bus for System Test and Emulation Host Port Interface LC57 BC57S. Source code upward compatible with all C1X, C2X and C2XX devices. Single 5V or 3.3V supply. Static CMOS technology. Memory 10K 16-bit words of on chip program data RAM C50. 2K 16-bit words of on chip program data RAM C51. 1K 16-bit words of on chip program data RAM C52. 4K 16-bit words of on chip program data RAM C53S. 7K 16-bit words of on-chip program data RAM LC56, LC57, BC57S. 2K 16-bit words of single cycle on-chip boot ROM C50, BC57S. 8K 16-bit words of single cycle on-chip program ROM C51. 4K 16-bit words of on-chip program ROM C52. 16K 16-bit words of on-chip program ROM C53, C53S. 32K 16 ROM LC56, LC57. Bit words of on-chip program ROM. Memory interfaces 16 programmable software weight state generators for program, data and input-output memories. 224K word, 16-bit maximum addressable external memory space, 64K word program, 64K word data, 64K word input-output and 32K word global. Packaging 100-pin TQFE C51, C52, C53S, LC56. 132-pin QFP C50, C51, C53. 100-pin QFP C52. 144-pin QFP BC57S. 128-pin TQFP LC57. TMS 320 LC57. BC57S host port interface. The host port interface HPI is an 8-bit parallel port available on the LC57 and the BC57S. The HPI provides a glueless interface to standard microprocessors as well as to other TI devices. The HPI appears as a 2K word block of shared memory that is available in either a FIFO or standard random access configuration. Most importantly, the HPI has the ability to maintain its high level of functionality as the interface between an external CPU and the C57 even while the C57 is idle or in reset. This significantly reduces system power consumption by offloading standard input-output tasks from the DSP. Features of the HPI include byte wide register addressability, 8-bit parallel port, high-speed back-to-back access, dedicated bus to 2K, 16-bit words of SARM, shared access mode SAM, normal mode of operation, allows DSP and host to have HPI memory access, asynchronous host access, resynchronized internally, 45.7 Mbps at 57 MHz, 64.0 Mbps at 80 MHz. Host only mode HOM home. allows host to access HPI memory while C57 is in idle 2 or in reset mode. 5 mA power dissipation idle 2, 160 Mbps independent of clock. TMS 320 LC56, LC57, BC57S buffered serial port. The buffered serial port BSP provides a no overhead mechanism to serially with codecs, ADCs, and other peripherals. The BSP supports 8, 10, 12, and 16-bit serial data packets and uses a 2K byte buffer to hold input or output data. Downward code compatible with the standard serial ports, the BSP is designed to be completely flexible and programmable. The BSP has the ability to simultaneously receive data from and transmit data to a programmable on-chip buffer through a dedicated memory bus, freeing the CPU to execute other tasks without memory bus contention. TMS 320 C5X multiplayer ALU features. The performance and parallelism of the C5X architecture become evident by studying the multiplayer and accumulator sections of the device. The on-chip multiplayer performs a 16-bit by 16-bit multiply with a 32-bit product in a single cycle. To double the performance, the C5X devices can fetch 2 data operands when executing the multiply and accumulate MAC instruction. Scaling and fractional math shifts occur in parallel with all arithmetic operations. The C5X devices are the first to include an accumulator buffer. The accumulator buffer provides quick comparisons to the accumulator contents to determine the minimum or maximum in a table of values, a common operation for both general purpose and DSP algorithms. This is very useful in implementing Viterbi decoding algorithms. Additionally, the accumulator buffer allows quick temporary storage of a commonly referenced value, eliminating the extra cycles it takes to store the value in memory. It also allows up to 65-bit shifts among accumulator buffer, and carry. Features of the C5X multiplier ALU include single cycle 16-bit into 16-bit multiply, yielding a 32-bit product. Ability to access program and 2 data operands simultaneously. Simultaneous ALU and multiplier operations performed by the CPU. Zero overhead shift registers. Accumulator buffer with path back into ALU. TMS 320 C5X parallel logic. The parallel logic unit PLU performs logical operations without corrupting the ALU contents. This allows data to be checked and decisions made without the overhead of storing and restoring the ALU content. The PLU supports AND, OR, XOR, and compare functions. These functions are commonly used to set, clear, and toggle bits within a data memory location. To make these functions easy to use, dedicated instructions perform them, using either immediate or register data to compare with the data memory location. Features of the C5X PLU are performs logical operations without disturbing ALU arithmetic registers, sets, clears, and toggles any number or combinations of bits in data memory, compares bits individually or collectively, supports long immediate and register values. TMS 320 C5X interrupts. The C5X supports 4 external interrupts, 2 serial port interrupts, 1 timer interrupt, and a trap instruction. To speed up interrupt service routines ISRS, the key registers are shadowed with a one level deep stack and are saved in a single cycle. This saves 22 cycles when an interrupt occurs by eliminating the need to push and pop these 11 registers. The C5X interrupt features include interrupt sources, 4 external, 2 serial port, 1 timer, 1 trap, 1 level deep stack on strategic registers for zero overhead context switching, program accessible interrupt flag register IFR for software interrupt polling, automatic global interrupt enable on return from interrupt service routine, relocatable interrupt vectors. TMS320 C5X circular addressing. Circular addressing is a method to address aging data sets for common DSP algorithms. For example, after performing the first set of calculations on a finite impulse response FIR filter data set, a new data value must be brought in and the oldest value discarded. Data move DMOV allows you to do this by treating data in a circular fashion with the oldest and newest values located side by side. At the end of each calculation, a new data value is placed in memory at the location of the oldest value. You update the circular buffer start address to correspond to the newest value and the circular buffer and address to correspond to the oldest value. Circular addressing features are 2 circular addressing data buffers, memory mapped auxiliary registers to indirectly address each circular buffer, effective use of data memory space to increase performance, repeat and block instructions. The C25 was the first device to offer a zero overhead looping instruction. The RPT instruction, the C5X expands this capability with the RPTZ and RPTB instructions. The RPTZ command is a logical extension of the RPT command that also clears the accumulator and product registers. This saves 2 cycles in typical routines. The repeat block instruction RPTB allows you to repeat a block of code up to 64k times without any overhead required to branch to the beginning of the code segment. This allows you to benefit from a faster instruction cycle due to the pipeline without paying a penalty for program discontinuity. TMS320 C50 and TMS320 LC50. The C50 and LC50 feature large on-chip RAM blocks which are ideal for form function emulation. The LC50 is the low voltage 3.3V version of the C50 device and significantly reduces power consumption. The C50 is a highly integrated DSP offering a complete system on a single chip with a boot ROM and 10K 16-bit words of on-chip RAM. An entire DSP can be integrated into a 132-pin QFP. By integrating the memory on chip, you reduce both power and board space. Integrating the off-chip memory can be especially important in high-performance systems to eliminate expensive high-speed static RAM (SRAM). The C50 offers 25 and 35 NS instruction cycle times and accepts source code from the C1X, C2X and C2XX generations. It has a full XX synchronous serial port, time division multiplexed TDM, communication port and a pre-programmed ROM boot loader. Other features of the C50 include a 192K word external address reach and ANSI compiler and an IEEE 1149.1 standard JTAG emulator control. TMS320 C51 and TMS320 LC51. The C51 features a user mask-able ROM for implementing information that was pre-programmed by TI. It is object code and pin compatible with the C50 device. The LC51 is the low voltage version of the C51. In the C51, the C50's 9K word block of RAM is replaced by 8K 16-bit words of on-chip ROM. This provides a considerable advantage in cost and performance for users who require large amounts of on-chip program space. With this ROM and 2K 16-bit words of RAM, sophisticated DSP algorithms can fit on a single device. This device is available in a 132-pin QFP and 100-pin TQFP measuring only 14 by 14 by 1.4 mm for designs that require both small board area and reduced height. The C51 is available in 3.3 volts or 5 volts and 35, 25 or 20 NS cycle times. It has communication ports similar to those of the C50 and has an optional pre-programmed ROM boot loader. The C51 accepts source code from the C1X, C2X and C2XX generations. It also has a full XX synchronous serial port and a TDM serial port. Other features of the C51 includes a 192K word external address, reach an ANSI compiler and an IEEE 1149.1 standard JTAG emulator control. TMS320C52 and TMS320LC52. The C52 is a cost-effective implementation of the C5X architecture. The LC52 is the low-voltage version. Traditionally, devices in the same price range have offered 10 MIPS performance. The C52 provides twice the performance at 20 MIPS and has room to grow into a 50 MIPS version. The 4K 16-bit words of ROM and 1K 16-bit words of RAM can be configured with your code or purchased pre-programmed with the bootloader. The C52 is available in 3.3 volts or 5 volts as 35, 25 or 20 NS cycle times. Comes in a 100-pin QFP and a 100-pin TQFP as a full XX synchronous serial port and as an optional pre-programmed ROM bootloader. The C52 accepts source code from the C1X, C2X and C2XX generations. It also has a 192K word external address, reach an ANSI compiler and an IEEE 1149.1 standard JTAG emulator control. TMS320C53 and TMS320LC53. The C53 and LC53 provide greater integration of on-chip ROM than the C51. The advantage of bringing memory on chip reduces power and board space requirements. On-chip memory also provides a considerable advantage in cost and performance. The 16K 16-bit words of ROM and 4K 16-bit words of on-chip RAM can be configured with your code or purchased pre-programmed with a bootloader. The C53 is available in 3.3 volts or 5 volts as 50, 35 or 25 NS cycle times. Comes in a 132-pin PQFP and has a full XX synchronous serial port and a TDM communications port. The C53 accepts source code from the C1X, C2X and C2XX generations. It also has a 192K word external address, reach, an ANSI compiler and an IEEE 1149.1 standard JTAG emulator control. TMS320 C53S and TMS320 LC53S. The C53S and LC53S are similar in most respects to the C53 and LC53 to accommodate the integration capabilities of the C53 into a 100-pin TQFP. Some features were removed from the standard C53. The C53S offers two standard serial ports instead of the TDM and standard serial ports in the C53. The C53 has reduced capability of the on-chip analysis block and has no boundary scan. The C53S offers 25 and 35ns instruction cycle times and accepts source code from the C1X, C2X and C2XX generations. Other features of the C53S include a 192K word external address reach, an ANSI compiler and an IEEE 1149.1 standard JTAG emulator control. The C53S also offers an optional pre-programmed ROM bootloader. TMS320 LC56. The LC56 provides greater integration of on-chip ROM than the C53 with 32K 16-bit words of on-chip ROM and 7K 16-bit words of on-chip RAM. The LC56 can accommodate large program and data spaces on chip, thereby minimizing off-chip access. The communications ports comprise a full duplex synchronous serial port and a very fast BSP with a dedicated bus. The BSP is capable of 40 Mbps at a 25ns instruction cycle time. The LC56 is optimized for high performance, low power applications. As a result, it operates at 3.3 volts only. The LC56 offers 25 and 35 numbers instruction cycle times and accepts source code from the C1X, C2X and C2XX generations. Other features of the LC56 include a 192K word external address reach, an ANSI compiler and an IEEE 1149.1 standard JTAG emulator control, a boot ROM option and a programmable PLL. The LC56 comes in a 100-pin TQFP. TMS320 LC57. The LC57 incorporates the same amount of on-chip memory on the LC56 and offers a high-throughput buffered serial port. In addition, the LC57 provides an 8-bit wide host port interface HPI, which can be used to communicate with other LC57 devices or embedded microprocessors. The LC57, like the LC56, is capable of 25ns instruction cycle time at 3.3 volts. The LC57 offers 25 and 35ns instruction cycle times and accepts source code from the C1X, C2X and C2XX generations. Other features of the LC57 include a bootload through the HPI or a standard serial port, a 192K word external address reach, an ANSI compiler and an IEEE 1149.1 standard JTAG emulator control. The LC57 also offers a boot ROM option, a full duplex synchronous serial port, programmable PLL, a BSP with a dedicated bus and an HPI with a dedicated bus. The LC57 is packaged in a 128-pin TQFP. TMS320BC57S. The BC57S takes advantage of the same peripherals that are on the LC57 to make the BC57S a cost-effective embedded data intensive applications engine. In order to provide a broad-based appeal, the BC57S differs from the LC57 in 4 ways. The 32K 16-bit words of ROM space has been replaced with a boot ROM. The BC57S can operate at 5 volt. The 144 pin package of the BC57S has a wider lead pitch than the package of the LC57. The BC57S is lower in cost. The BC57S offers 25 and 35 ns instruction cycle times at 5 volt, accepts source code from the C1X, 2X and C2XX generations, and has 7K 16-bit words of RAM. Other features include a 192K word, external address reach, an ANSI C compiler, and an IEEE 1149.1 standard JTAG emulator control. The communication ports include a full duplex synchronous serial port, an HPI with a dedicated bus, and a DSP with a dedicated bus. The LC57S is packaged in a 144-pin TQFP. Conclusion. In this chapter, the user would learn the following in detail. TMS 320 C40 bar 50. Analog devices.